So in this chapter of this tutorial, we are going to address hybrid cloud mobile edge computing setups. In particular, we're going to look into hybrid networks which utilize the concept of rate splitting. We're also going to look at XR device cooperation over such networks which utilize cooperative NOMA. So here is a picture illustrating such a hybrid network. So we have both the cloud as well as mobile edge users, basically, which support in particular those cell edge users. So in this chapter, the content is going to be as follows. So as we have moved on from CRAN to multi-cloud CRAN, we are doing one step more to address hybrid networks. When we look at the architecture of such hybrid networks, we have to design a joint communication and computing framework. And the techniques we are going to use to solve the problems we are going to face fractional programming, in which we use the concept of quadratic transform. So what were the challenges and limitations of CRAN and multi-cloud RAN? First of all, basically, multi-cloud RAN encounters problems such as poor service quality, in particular at cell edges, because there we suffer from interference and perhaps weak received signal power. The current framework we developed so far basically only tackles communication resources only, and that actually limits multi-cloud RAN applications in many 6G use cases. So when we look at the resilience of multi-cloud radio access networks, then they have the advantage that we are able to perform virtualized and flexible network functions at the central processors, and they don't have a single point of failure because we have multiple clouds available, and this makes them more resilient. However, the architecture is quite inflexible in terms of access, computing, and varying quality of service needs, as we have a single entire architecture. So that motivates basically to first of all deploy UAVs, uncrewed aerial vehicles, basically at the edge to support the users at the edge, and this also shows that we need to extend basically the framework for communication also to into such an extent that we are able to capture the computing perspective. So with respect to the lack of flexibility, so we need to add an extension to cover both cloud and also the edge tier. And this ends up basically into a hybrid network, which is basically UAV aided, in which basically both the cloud and the mobile edge is utilized in terms of computation and communication to provide the required quality of services for the desired users. Here are some relevant works related to the chapter. In particular, the works mentioned here basically are used as the basis for the chapter of the tutorial. So if you are interested in more details, please don't hesitate to check those articles, and in case you have further questions, then you can always reach out to us. So now let's look into the details of this hybrid network architecture, which actually is a multi-tier setup with multiple servers. So first of all, we have the cloud tier localized at the central cloud, and then we have the edge tier illustrated in this form as UAVs. We have distinct sets of radio access resources which we can utilize for the overall objective. So this allows us to perform flexible distributed optimization of the system variables, both in terms of communication and computation. One aspect which has to be addressed basically is the communication overhead between the central cloud and the UAVs, which is done in such a way that it does not consume too many valuable resources. The challenge here in the setup, as you can see here, is that we have two kinds of interference. We have, first of all, the cloud UAV interference, which is shown in as those dashed lines here and here. But we also have the intra-cloud interference illustrated here between the base station and the user in the neighboring cell. Now, how can we perform communication and computation jointly in such a system? We make use of this cloud edge computing based architecture, in which we have a very powerful and scalable central cloud as a central processor. In addition to this, we have embedded edge users at the uncrewed aerial vehicles, which jointly with the central processor serve computation-hungry devices in the network. Now, the task of the network is now to utilize this communication capabilities such as device association, beamforming, and power control, as well as its computing capabilities such as CPU cycles allocation, to provide the quality of service to the users such that basically they can perform the task basically given to them. Applications which can imagine for instance, XR video processing, digital twinning, and so on. So the system model we have consists of a central cloud shown here, and capital E edge computers which are located at capital E UAVs, and we basically perform downlink in such a network serving in total capital K users with the support of capital B base stations. So we assume for now that we have a predetermined user association, and we also assume that we have full channel state information at the transmitting units. Now the resources we have to manage are as follows. So first of all, we have the beamformers to design at both the base stations given as WBK and the beamformers at the edge computers given as W tilde EK for each user K. So in addition to this, we have to design the base station user clustering, and we have to decide upon the computation allocation given here by FK, essentially the cycles per second we allocate to the task needed to be done by user K. In addition to this, we have to determine and allocate the data rates to the individual users K given here by RK. So the system performance is then a function which depends on the beamformers. Here the computation allocation and of course the data rates. Before we move on, we have to address the consumption of power in this network, because we have two different communication units, the base stations and the edge computers. Therefore, we need two power consumption matrices. The power consumed by base station B is denoted as PBCC, while the power consumption at the edge computers E is denoted as PEEC. When we look at the power consumed by the base station, basically, which essentially boils down to the communication only, we see that we are summing up over all users which are served by the central cloud of the beamforming vectors, in particular over the L2 norm squared of the beamformers. The power consumption at the edge computers are a bit more complicated, because in addition to the communication towards all users which are served by the edge computers, we have also power consumption due to the computation and the operational power consumption. So now this QE is assumed to be fixed, and it essentially accounts for all flight-related mechanical power and operation power consumption. The terms SE and μE are assumed to be constant and depend on the assumed CPU model. So we see that we have to balance between the communication and the computation resources in this network. In such networks, the delay within the network is very important, and therefore we have to define the overall user delay, here given at theta k. And the user delay is a superposition of three components. First of all, the delay due to the computation, essentially to process the tasks of the user. Then the frontal delay, which is here the worst case frontal delay for all base stations serving user k. And then we have the transmission delay given here, basically to transfer the data wirelessly to the user. So the computation delay is given as a function of capital Fk, which represents the total computation cycles required for user k's task, and is divided basically by the allocated computation cycles Fk, which basically tells us the cycles per second needed to perform user k's task. So similarly, the transmission delay is also given as a fraction of the dk, which represents the data size for k, and the data rate in bits per second, which is basically allocated to this particular user. So the allocation of the resources in order to maximize the overall objective can be formulated nicely as an optimization problem, which is illustrated here. So we set our goal to maximize the weighted sum rate by basically using the variables like the beamformers, like the computation cycles and the rates, under the constraint that the frontal capacity is limited per base station, that we have a maximum computation capacity per central cloud and per edge computer. We have an achievable rate requirement per user. We have a maximum transmit power constraint for each base station. We have a maximum power consumption available basically at the edge nodes, and we have a delay constraint which we have to fulfill for each user. To be more specific, we have here the weighted sum of the rates Rk, where the weights are given by alpha k for each user k. We have the maximum transmit power constraint per base station, where we sum up the L2 norm squared over all users which are supported by the central cloud. Then we have the constraint for the maximum power consumption at edge computers or UAVs, and we have the delay constraint for the central cloud users and edge computer users, where this TK denotes the maximum tolerable delay per user. So now, due to the nature of the norms we are using here and the non-convexity of the overall feasible set, this problem is a mixed integer non-convex optimization problem. And as such, those problems like this are generally difficult to solve. And in the following, basically, we propose a series of problem reformulation so as to devise basically a numerically practical algorithm to solve this problem. So one of the challenges is given by the constraint with respect to the rates. So this highly coupled and fractional SCNR expression here with the concave logarithm prevents essentially like us from finding a solution to this overall problem in an efficient way. And one way basically to avoid this is to introduce an auxiliary variable, and with this we are able to reformulate this complicated constraint, and are able to simplify the optimization problem. So this is done here. So we introduce this auxiliary variable given by gamma k, where gamma k is then upper bounded by the SCNR expressions we had before. So now we move on to the next step and rewrite the fraction which we had on the previous slide. So by utilizing the general fractional programming framework developed in this work here, we applied the quadratic transform in its multidimensional and complex form to decouple essentially the numerator and the denominator of the fractional constraint, which we had on the previous slide, as given here. And here we have those auxiliary variables uk, which are basically complex valued vectors. Now, so this is a convex function with respect to the beamforming vectors w in case the auxiliary variables u are fixed. And interesting enough, basically the optimal UK for fixed beamformers W can be written in closed form as given here, basically, which is essentially obtained by setting the partial derivative of the gamma k respect to UK to 0, and then solve for UK. And this is basically the solution you get, which you iteratively update by optimizing first for WK while keeping UK fixed, and then optimizing UK while having WK fixed. After having reformulated this problem in this convex fashion, we are now able to provide an algorithmic solution. First of all, for the user to server association, we use a proximity-based approach. This is one approach among other possible matching heuristics. We could have also applied a generalized association problem-based solution, as we have done in the previous chapters. So regarding the allocation of rates and computing regarding the beamformers and the base station clusters, we propose to use an iterative algorithm, which is illustrated here. So after initialization of the beamformers and other variables, we update auxiliary variables, and then we try to solve the optimization problem either by MATLAB or any other tools like CVX. And then once basically we get an update on the optimization variables, we update the auxiliary variables and then do another round of iteration, and then we proceed until the convergence. Alternatively, we can apply a decentralized approach, basically where we try to first get a solution for each component as illustrated here. And then there's the next step where the information exchange between each component is performed, so between the cloud and the edge computers, basically. And then we move on to the next iteration and updates the auxiliary variables. This is going to be talked in detail again later in the tutorial. Now let's have a look at some simulation results. First, we want to understand what is the impact of the number of UAVs on the overall performance. So what we are going to do is we are going to compare the proposed scheme with a fully centralized protocol referred to as FCP, or a fully distributed protocol, FDP. Recall that the proposed protocol is a distributed protocol, but we have some information exchange. The simulation has been done assuming that we have in total 30 users. We have 7 base stations, each equipped with 3 antennas. So here's the plot. So we see the average rate per user in megabit per second over the number of UAVs for different backhaul constraints. So this is for 25 megabit per second. That's for 50 megabit per second in purple and in dark blue for 75 megabit per second. So we see naturally that the more we relax the frontal constraint, the higher the average rate of each user gets. More interestingly is that we see that for all the cases that or proposed scheme, basically the proposed distributed protocol, that it performs in between the fully connected one or fully centralized one and the fully distributed one. In particular, basically we see that so when we zoom out, when we look at this regime, basically that as the frontal gets less and less to be the bottleneck, basically, or distributed approach basically performs as close as a fully centralized approach. So when we now look at the number of the UAVs and the impact on the average rate, we see that basically we have a significant improvement in comparison to the case where we don't have any UAVs. And we see that naturally, basically, by increasing the number of UAVs, we are able to increase the average rates per user more and more. It means that satellite users are benefiting by adding more and more UAVs into the system. Now let's have a look on the impact of the delay constraint. That means the dynamic it causes. For this, we look at the worst case delay versus the ratio of the data size and computation cycles per task. Regarding the parameters, we assume that we have 4 edge computers. That means 4 UAVs. We have 12 users. We have in total 7 base stations, each equipped with 2 antennas. The plot we get is as follows. Here we have the delay versus the fraction of dk over fk, so data size over computation cycles. And we have investigated this for 2 cases. First of all, so we set the maximum tolerable delay constraint to tk to 500 milliseconds, and then later on to 1300 milliseconds. So which is shown here in purple, while the first one is shown here in pink. So we see that given this delay of 500 milliseconds, we see that as we increase this ratio, the transmission delay becomes more dominant, while when we decrease this ratio, the delay is mainly caused by the computation time. So we see that this effect basically, or this dynamics, increases even more if we have a higher delay constraint given by 1300 milliseconds. So we can nicely see that there's a trade-off in the system, capability we can utilize. That means we can adjust the communication and computation resources in a dynamical way. We would like to close up this chapter here by talking about the challenges and limitation of such hybrid cloud mobile edge networks. So those networks encounter problems such as enhanced susceptibility to interference due to those additional use of the edge computers that happens within the cell as well as at the cell edges. We have an increased resilience within those hybrid networks because we have virtualized functions and as well as flexible network functions, both the central cloud and this edge computers. That means similar to the multi-cloud setup, there's no single point of failure. However, the issue is that we have an unflexible and non-robust access scheme, which is based on spatial multiplexing, essentially beamforming, which relies heavily on perfect channel state information. And we treating interference as noise. So as a remedy to those issues, we could focus on mitigating interference. And in particular, we could try to partially decode interference and partially treat it as noise, as is done in rate splitting concepts.